Take a wire of very pure metal, hang it in a cryostat, and cool it towards absolute zero while you keep measuring its resistance. The resistance falls, and then it stops falling. It levels out at a small value that never goes away, set by the impurities that were in the metal when you bought it. Now subtract that flat floor off and keep only the part the temperature is responsible for. Plot it against temperature and you get a curve that tells you nothing. Plot it against temperature multiplied by itself and, in the right metal below about 10 Kelvin, you get a straight line through the origin. A power of exactly 2.
Which is a strange thing to find in a lump of metal, because nothing you can point at in one obviously has a 2 in it. That exponent is not the outcome of a fit. It is a count, and what is counted is empty seats. Before we are done, you will have done it yourself. But I am not allowed to start there, because I walked in owing you 3 things, and you should collect them first.
I intend to. You made a claim last time and were careful to say it was not yours to make, that the excitations of a metal with strong repulsion are in one-to-one correspondence with those of a gas of electrons that ignore each other. Heavier, shorter-lived, carrying less weight, but structurally the same. Then you said nothing you had built implied it, and put 3 conditions down. 1. The correspondence has to survive turning the interaction on, with no states appearing and none vanishing. 2. The thing has to live long enough to deserve being called a particle. 3. All of it is confined to low energies near the Fermi surface, and you owe me a statement of how near.
All 3 in that order. And I will warn you that the first and third turn out to be the same condition in different clothes. Start with the first, because it is genuinely an idea rather than a calculation, and I think the most underrated argument in the subject. It is called adiabatic continuity.
Set it up then. What is the thought experiment?
A metal with a dial on the side. At one end, the electrons do not see each other at all. A Fermi see every state known, every excitation, one electron lifted out and set down above the shoreline, leaving a hole behind. At the other end, the Coulomb repulsion is at full strength. 6 electron volts between neighbours, the scandal this series opened with. Turn the dial slowly from one end to the other and watch what becomes of the states.
And slowly is carrying weight in that sentence.
It is carrying all of it, and there is an old, clean theorem behind it. Born and Fock, 1928. If you change a Hamiltonian slowly enough, slowly compared with the gap between the level you are in and its neighbours, then a system that starts in the third state ends in the third state. Not the same state. It deforms, sometimes past recognition, but it never jumps across to another, and no new state appears underneath it.
Give me a picture, because the third state is bookkeeping, and I want an object.
A guitar string. Pluck it, and it rings in its fundamental, or in the mode with one stationary point in the middle, or the one with 2. Now turn the tuning peg very slowly, and wrap a bit of tape round the string while you are at it. Every frequency shifts, and the shapes distort. The stationary points slide. They stop being evenly spaced. The sound is not the sound you started with. But the mode with 2 stationary points still has 2. You can follow it the whole way and count it at the end. A node cannot be created by a smooth change. It would have to arrive from nowhere.
So the label survives, even when the thing it names has changed out of all recognition.
That is the entire move, and Landau's idea is that sentence applied to a metal. The free gas has excitations labelled by which momentum state you emptied, which you filled, and the spins. Turn the interaction on slowly, and each of those deforms continuously into a state of the real metal. No longer one electron in one momentum state, but that electron plus a rearrangement of every other electron in the crystal, a hole dug around it and a wake behind it, and it still carries the label it set out with. That labelled object is the quasiparticle.
Let me say that back because it is more radical than it sounds. You are not claiming the interacting system contains something resembling an electron. You are claiming its states can be put in a list, and the list is the same length with the same labels as the free system's list. The correspondence is the claim. Any resemblance is a consequence.
That is the right emphasis, and it is why this is about counting rather than similarity. Landau is not saying the electrons stay nearly free. He is saying that however violently they rearrange, no new low-lying states are manufactured and none destroyed. So the catalogue survives. And a catalogue is a cheap thing to preserve. It survives changes that would destroy any picture you could draw.
Now let me be difficult where I think this is weakest, because I do not believe that theorem applies here. Born and Fock need the change to be slow compared with the gaps. In a lump of metal, the levels are spaced by something like the Fermi energy divided by 10 to the 23. There is no process in the universe slow compared with that, so the theorem you quoted is void in the only case we care about.
Void as stated, and I would rather you caught it now. 2 repairs. First, you do not have to follow every state. States are sorted by conserved labels, momentum, spin, particle number, and an interaction that does not know where the origin is cannot move a state between sectors. So the question is never, does this state get confused with the 10 to the 23 next to it? It is, does the lowest state carrying this momentum and spin stay the lowest state carrying it? Far weaker.
And the second repair.
A timing argument, and it is where your third condition sneaks in early. To make an excitation of some small energy above the surface and follow it adiabatically, the switching has to be slow compared with that excitation's own oscillation period. Planck's constant over its energy. But it also has to be fast compared with its lifetime, or the thing decays while you are still turning the dial.
So I need a window, longer than the oscillation, shorter than the death. And the window only exists if the excitation rings many times before it dies.
Only in that case, and the whole of Fermi liquid theory lives inside it. So my first condition is not independent of my second. And the reason the theory works is that the window does not merely exist. It widens without limit as you approach the shoreline. Hold that until we do the count.
Fine, but name the failure modes, because a hypothesis with no stated way of failing is worth little.
3, and they are concrete. 1. A bound state forms. If 2 electrons find it favourable to bind into a pair as you turn the dial, a state has appeared below everything in the free catalogue with no counterpart in it. That is a superconductor, not a Fermi liquid with odd parameters, but a different catalogue. 2. A gap opens and the low-lying excitations are not deformed but removed. That is a Mott insulator, which is what the Hubbard model does at 1 electron per site with a large enough penalty. 3. The quiet one. The perturbation may be singular, arbitrarily small, and still able to change the answer if the unperturbed system is exactly poised.
And I suspect you are about to tell me the third actually happens.
It actually happens. Walter Kohn and Joachim Luttinger showed in 1965 that a Fermi liquid of electrons that purely repel, no attraction anywhere in the problem, is nevertheless unstable to pairing at low enough temperature. The Fermi surface is so sharp that the screened interaction develops faint wiggles at long range, which is where last time's exponential screening was an approximation, because the exact response leaves an oscillating tail behind it, and somewhere in those wiggles there is an attractive channel. So strictly, the normal Fermi liquid is never the true ground state of anything.
That sounds like it demolishes the whole thing.
Except for the number. The temperature where it matters is one nobody will ever reach. The published estimates run down to around 10 to the minus 40th of a Kelvin. So, the ground state of a real metal is not a Fermi liquid, and this will never be observed by anybody. Both halves are true, and the second is the one you use.
Then let me state adiabatic continuity in my own words, without your apparatus, because if I cannot do that, I have not got it. I take the system I can solve, electrons that ignore each other, and turn the interaction up gradually rather than switching it on. Because the change is gradual, each state slides continuously into a state of the real system, and I can keep a finger on it the whole way. Nothing new is born, nothing dies, so at the end I have the same number of low-lying states as I began with, wearing the same labels. What I have lost is the right to say what any of them looks like. What I have kept is the right to count them.
And keeping only the counting buys you the whole subject. A theory of a strongly interacting liquid, written in the vocabulary of a gas, with a small number of unknown coefficients you go and measure. Everything from here is unpacking that.
So unpack the coefficients. If the labels survive, what is actually allowed to change?
Work it out before I tell you. You have enough. The quasiparticle inherits a label from a free electron. Sort the properties of that electron. Which are you certain survive, and which are up for grabs?
Charge survives, exactly conserved, in whole units, so it cannot drift a little as I turn a dial. Spin survives for the same reason, quantized in halves, and half cannot continuously become slightly more than half. Momentum survives as a label because the interaction does not know where the origin is, so total momentum is conserved as I turn it on. What is left is the relation between the momentum label and the energy, how much it now costs to make an excitation carrying that momentum. That is the only thing that can change.
That is the list, and you have just derived what parameters Landau's theory is permitted to have. Now narrow it. We only care about excitations very close to the surface, so we do not need the whole energy-momentum relation, only its behavior in a thin shell. And over a thin enough shell, any curve is a straight line.
So the whole content is one slope, how fast the energy climbs as I move outwards through the Fermi surface.
One slope. And a slope of energy against momentum has the dimensions of a velocity, the Fermi velocity, the speed at which excitations at the surface actually travel. And a momentum divided by a velocity is a mass. So the single number describing what the interaction has done to the motion of these things is a mass, and it is not the mass of an electron.
Give me the picture, because effective mass is a phrase people use to avoid explaining themselves.
An air bubble rising in a glass of water. It weighs essentially nothing. It is air, so a nudge ought to send it flying. It does not. It is sluggish for a reason you can compute. To move the bubble, you must move water out of its path in front and let water close in behind, and that water has to be accelerated too. Work out how much, and the bubble responds exactly as though it carried a mass of about half the water it displaces. Standard hydrodynamics, not a figure of speech.
So the bubble did not get heavier. The bubble plus the flow it is obliged to drag is heavier.
And nothing about that is approximate. If you only ever push bubbles and watch them respond, the mass you report is the honest answer to every question you can ask by pushing bubbles. The electron in a metal is in that position. It cannot move without the other electrons getting out of the way, and their getting out of the way costs energy and takes time.
And how do I measure it? A mass I cannot get at is a story.
With heat. Cool a metal to a few Kelvin and measure how much energy it takes to warm it slightly. Two things contribute. The lattice vibrations give a term dying as the cube of temperature. I am skipping why it is a cube. What it would show you is a count of how many vibrational modes are soft enough to be awake at that temperature. The electrons give something else, and its shape is yours if you want it. How many electrons in a metal can absorb anything at all?
Only the ones within about a thermal energy of the shoreline, Everyone deeper has no empty state to move into and is locked in by Pauli. That was the 0.33% in copper. So the number taking part is proportional to temperature, and each takes up about a thermal energy, so the stored energy goes as temperature times temperature. Heat capacity is the rate at which stored energy changes with temperature, so differentiating knocks one power off. The electron term is a straight line in temperature,
which is a promise from the first hour, repaid. Plot the heat capacity divided by temperature against temperature squared. The lattice piece is the slope, the electron piece is the intercept. Every undergraduate laboratory does it.
and the coefficient gives me the mass how?
It is proportional to the number of states per unit energy at the surface. Flatten the energy-momentum relation, make the particle heavier, and the same range of momentum spans less energy, so the states pack more densely and the coefficient is bigger. Measure it, divide by what a free gas of the same density would give, and the ratio is the mass enhancement. No model in between.
Give me numbers from mild to absurd.
Mild, the alkali metals, 1 loose electron per atom. Potassium comes out about a quarter heavier than free, cesium about 40% heavier. Middling, strontium ruthenate, a layered oxide and about as close to a textbook Fermi liquid as a strongly correlated material gets. Quantum oscillations give quasiparticle masses running from about 3.5 to about 15 times the mass of a free electron, depending on which sheet of its Fermi surface you stand on. Same crystal, same electrons.
And absurd.
In 1975, Klaus Andres, John Graebner, and Hans Ott measured the low-temperature heat capacity of a compound of cerium and aluminium and found an electronic coefficient about 1,000 times an ordinary metal's. Read as a mass, that is a quasiparticle weighing roughly 1,000 electron masses. Those materials got the name heavy fermions.
Stop, because that number should have broken something. 1,000 times heavier, and you are still calling it a Fermi liquid.
Still a Fermi liquid, and that is what ought to astonish rather than the number. Those compounds have a heat capacity straight line in temperature, a resistivity going as temperature squared, and a Fermi surface whose volume is what electron counting says. Every structural prediction Landau makes, they obey, with a parameter 1,000 times off the naive value, which shows the parameter was never the point. The catalogue was.
And the catch?
Temperature. Heavy Fermion compounds behave this way only below a coherence temperature, often around 10 Kelvin. Warm them above it, and the quasiparticles come apart. The same material then looks like a lattice of independent magnetic moments with some ordinary electrons wandering past. So the Fermi liquid there is a property of a regime, not of the material. I would rather say that than let you carry away that heavy fermions are metals with a big number in them.
Now the other number. 3 times now you have said a quasiparticle carries less weight than a bare electron, and I have let it pass 3 times, and I have no picture for it at all. Less weight of what?
We will build the picture and name it at the end. Start with an operation you could genuinely perform. Take your metal and put 1 extra electron into it with a definite momentum. In a laboratory, tunnel 1 in through a barrier. In the free gas, what have you made?
An exact eigenstate, definite energy, sits in that momentum state, nothing ever happens to it.
Now do it in the real metal. A bare electron dropped into a sea that was minding its own business is not an eigenstate of anything. Expand it in the true excited states and ask where the amplitude went.
Some lands on the single quasiparticle with that momentum, since that is the state which inherited the label. The rest lands on messier things. A quasiparticle plus an extra particle whole pair plus 2 pairs, states with the same total momentum, but the energy shared among several objects.
And the shares are what we are after, the fraction of the injected electron that emerges as the single clean excitation rather than the mess. It lies between 0 and 1, and in an interacting metal, it is not 1.
Give me the avatar.
Hit a piano string with the hammer. Some of the energy goes into the note, long, clean, a definite pitch. The rest goes into the thump of the hammer, the flexing of the soundboard, a hiss that is over before you have heard it. Record it and look at the spectrum, a sharp line sitting on a broad hump. The line's share of the total is a number between 0 and 1. Nobody thinks the note is fake because the hammer also thumped.
So, an electron injected into a metal is mostly the note and partly the thump.
And the note's share is the number I owe you. Now a second picture of the same quantity, because this one you can almost see. Go back to the free gas at absolute 0. How many electrons occupy each momentum state?
A cliff. Every state inside the Fermi surface holds its 2 electrons. Every state outside holds none, and the drop between them is vertical and happens exactly at the Fermi momentum. That is the C, drawn as a graph.
Now turn the dial. The interaction knocks electrons out of the C and leaves holes behind, so states above the surface become occupied and states below stop being full. The cliff erodes into a slope. The whole question, is whether anything vertical survives.
I would guess not. 6 electron volts against 7. I would expect it ground down into a smooth hill with no edge anywhere.
The cliff does erode, but a vertical drop survives at exactly the Fermi momentum, a genuine discontinuity at 0 temperature, however strong the repulsion, provided the system is a Fermi liquid at all. And the height of the surviving step is the same number as the note's share of the piano string. Arkady Migdal proved that in 1957 in a 2-page paper, and I am not going to prove it here. What the proof shows is that the coherent part of the excitation has nothing to occupy on the far side of the surface, so its whole share is deposited at the crossing rather than spread smoothly through it.
Name it.
The quasiparticle weight. Everybody writes it as Z, and it means what your 2 pictures mean. How much of a bare electron is left in the dressed excitation, and equivalently, how big a jump survives at the Fermi surface.
In words I would use in an exam. Z is the overlap between the real, dressed excitation and a bare electron of the same momentum, amplitude squared. 1 means nothing happened. 0 means the bare electron has essentially nothing in common with anything the system can actually do.
Right, and the numbers are more interesting than people expect. In sodium, the standard test case, the best calculations put it around 2/3, so 1/3 of a sodium electron is already not in the quasiparticle. In the metal people hold up as the example of nothing interesting happening. In a heavy fermion compound, the weight is of order 1,000th, and in 1 dimension it is exactly 0 at any repulsion, however weak. Not an arithmetic failure, but a genuinely different state of matter, and we come back to it.
My second debt, and I want it now because I got most of the way to it last time and you would not let me keep it.
You reached the right answer by the right instinct, and I stopped you because an instinct is not a count, and the conclusion matters too much to hold on credit. So count it. I will not do it for you. I will only stop you if you drop something.
Set the scene and I will count.
1 quasiparticle, a small energy above the shoreline, small compared with the Fermi energy, which is 7 electron volts in copper. How fast does it decay? What is it allowed to do?
It cannot simply shed its energy and drop into the sea because there is nowhere to drop to. Everything below is occupied. Ignoring the lattice and impurities, the only thing available is a collision with another electron. So 4 states are involved. My electron and its partner going in, and the 2 states they end up in.
4 states. Count the freedom and be careful which constraints are physics and which are Pauli.
The partner must come from below the surface, because above it there is essentially nobody to hit. But the partner also has to end up somewhere, and everywhere below is full, so it must finish above the surface. That means it has to climb over, and the only energy available to lift it is what my electron brought. So the partner cannot be dredged from deep in the sea. It must have started within one excitation energy of the surface.
First factor. Say it geometrically.
A shell. Not the whole sea. A thin shell just under the Fermi surface, whose thickness in energy is the excitation energy itself. The number of available partners is proportional to that thickness, one factor of the energy.
Now the outgoing pair.
Both must land above the surface because below is full, and energy is conserved, so between them they have exactly what came in, shared out. One of them can take anything from nothing up to the whole amount, and once I choose that, the other takes the remainder. So there is exactly one free choice left, and its range is again the excitation energy.
And the fourth state?
Not free at all. Energy conservation fixes its energy, and momentum conservation fixes where it points. So, of the four states, one is the electron I started with. One is pinned by conservation, and two are free, each ranging over an interval proportional to the excitation energy. Two independent squeezes. The rate goes as the energy multiplied by itself, the square.
That is the argument done properly, and it is yours. Now the second half, the half that actually matters and which almost nobody states. You have a rate. Compare it with something.
With what?
With the excitation's own energy. A rate has units of 1 over time. Multiply by Planck's constant and it becomes an energy. The width, the fuzziness in the excitation's energy. Put that next to the energy itself and ask which is bigger.
The width goes as the energy squared, the energy goes as the energy, so the ratio goes as the energy, and that vanishes as I approach the Fermi surface. So it is not merely that the excitation lives a long time, it lives a long time relative to its own clock. The fuzziness shrinks faster than the thing it is fuzzy about.
That is the most important sentence in this conversation. Say it once more in the language of a particle rather than of ratios.
A quasiparticle at high energy is a bad particle. It decays before it has finished being itself. Move it down towards the Fermi surface and it becomes a better particle, without limit. Not asymptotically adequate, asymptotically exact.
And there is your third condition answered. There is no sharp boundary, and there was never going to be one. The theory is not valid below some line and invalid above it. It degrades continuously, and the parameter controlling the degradation is the excitation energy divided by the Fermi energy, which is the small parameter this series opened by telling you did not exist.
Say that again, because it is a genuine reversal. In the first conversation, you showed me there was no small parameter. The interaction is 6 electron volts, and the Fermi energy is 7.
There is no small parameter in the interaction. There is one in the excitation energy, handed to you free by Pauli exclusion, with nothing whatever to do with how strong the repulsion is. That is how a strongly interacting metal behaves like a weakly interacting one. The expansion is not in the coupling. It is in how close to the surface you are looking.
Let me do arithmetic so I can feel it. Copper, Fermi energy 7 electron volts.
Do it as a count of oscillations. How many times does the thing ring before it dies? That is its lifetime divided by its own oscillation period, and the period is Planck's constant over its energy.
The lifetime goes as 1 over the energy squared, the period as 1 over the energy, so the ratio of the two goes as 1 over the energy.
And with the constants put in, It is simply the Fermi energy divided by the excitation energy times a factor of order 1 the counting cannot give you, which is reasonable because the Fermi energy is the only other energy in the problem. There was nothing else the ratio could have been built from.
So at room temperature, the relevant energy is thermal, about 25 thousandths of an electron volt. 7 divided by that is nearly 300. A thermally excited quasiparticle in copper oscillates a couple of hundred times before it dies.
And at a milli-electron volt above the surface, 7,000. At a microelectron volt, 7 million. Nothing has to be tuned, and nothing has to be small. You only have to look near the surface, and the surface is where every ordinary experiment is looking anyway.
And I should name what the count did not give me.
Name it, and I will say what it would take. The count gives the exponent, the 2, and nothing else. The coefficient in front needs the strength of the screened interaction between 2 electrons at the surface, integrated over directions, a real calculation with a real matrix element in it. What it shows is that the coefficient varies enormously between materials, while the exponent does not budge, which is what makes the exponent the interesting part.
And there is a hidden assumption in what I did. I counted a shell of states below the surface and a range above it. That used the fact that the Fermi surface is a surface, a two-dimensional thing bounding a volume.
It did, and I am glad you found it, rather than being told later. In one dimension, the Fermi surface is not a surface, it is 2 points. Count the phase space there, and your 2 squeezes collapse. There is essentially only one way to collide while conserving both energy and momentum, and the argument changes character entirely. That is why one dimension is a different world, and why the weight there is 0 rather than small.
Bring me back to the wire I started with. I have a rate going as temperature squared. Do I have the straight line?
Not yet, and the gap is worth an argument. At finite temperature, the typical excitation energy is thermal, so the collision rate between quasi-particles goes as temperature squared. Fine, but a collision rate is not a resistance. 2 electrons colliding conserve their total momentum exactly, and the electrical current is essentially the total momentum of the electron system. A collision that conserves total momentum cannot degrade the current.
So electron-electron scattering on its own produces no resistance whatsoever. It shuffles momentum among the electrons and leaves the sum alone.
None at all. Something has to take momentum out of the electron system, and the only thing available is the crystal. Here is the picture. 2 skaters collide on a rink and shove each other about, and however hard they shove, the pair keeps drifting the way it was drifting. Now put the rink inside a railway carriage with seats fixed at regular intervals. Most collisions still leave the pair drifting, but every so often the pair ends up hard against a seat and the carriage takes the shove, and the carriage is bolted to the ground.
And the regular spacing is doing the work in that picture, not the seats being solid.
The regular spacing is everything. Because the lattice is periodic, it cannot absorb any momentum you like, only whole units set by the spacing of the atoms. So a collision either conserves electron momentum outright and does nothing to the current, or hands over one of those fixed lumps and takes a real bite out of it. There is no small version. Rudolf Peierls named those umklapp processes, a flipping over, and they are what turns electron collisions into resistance.
Let me say that back because it is the join between my count and the wire I walked in with. Electrons hitting each other cannot slow a current down because the current is their total momentum and they conserve it between themselves. The only collisions that resist are the ones that shove a whole lattice-sized lump of momentum into the crystal, and the crystal is bolted to the bench. So the law needs 2 things, not 1. The phase space count says how often electrons collide, and umklapp says what fraction of those collisions costs the current anything. The exponent comes from the counting, the resistance comes from the lattice.
That is the join, exactly. And the law is older than Landau's theory. Weber at Bristol, 1937, working on the anomalous low-temperature resistance of transition metals, argued that electron collisions would give a term going as temperature squared. Though his own mechanism was different, light electrons dumping momentum into the heavy ones. P. Earle's umklapp is the version that survived. So the exponent predates Fermi liquid theory by 20 years. What the theory added was the reason it is exactly 2.
And where do I actually see the line? You were careful to say the right metal when I opened.
Because in an ordinary metal, the low-temperature resistance is dominated by electrons scattering off lattice vibrations instead, and that dies much faster than the square. As the fifth power of temperature, the Bloch-Gruneisen result. I am skipping why it is 5. What it would show you is 3 separate powers from how many phonons are awake, how much momentum each can deliver, and how little of that momentum points usefully backwards.
But it dies faster, so at the very bottom, the square should win.
At the very bottom, the square wins, and above that window, the phonons bury everything. So you see it cleanly in the transition metals, in strontium ruthenate, below about 25 Kelvin, and best of all in the heavy fermions, where the mass is so large, the electron-electron coefficient is enormous.
And that can be checked because I now have 2 independent handles on the effective mass, heat capacity, and resistivity.
It was checked, and it is one of the tidiest facts in the field. Kazuo Kadawaki and Stuart Woods, 1986, plotted the coefficient of the temperature squared resistivity against the square of the heat capacity coefficient for a long list of heavy fermion compounds spanning orders of magnitude in both, and got a straight line.
Which it should be if both are just reporting the mass. The heat capacity coefficient goes straight as the mass, that is, the flatter dispersion, packing more states into an interval of energy.
Now the resistivity coefficient, and take it in one step at a time.
The scattering rate goes as the mass, for the same reason, more states to scatter into. And then a heavier carrier responds less to the field it is being pushed by, which is a second factor. So the resistivity coefficient carries the mass twice over, and dividing by the heat capacity coefficient squared cancels it out completely.
And that cancellation is the whole content of the plot. It tests the framework and not any material. The individual numbers vary by a factor of 1,000,000, the combination does not. Which is what it looks like when a theory with unknown coefficients still has predictive content. It constrains relationships between measurements even where it cannot produce either measurement.
I want to examine something we have leaned on all hour without looking at it. You keep saying near the Fermi surface, as though the surface was still sitting where free electron theory put it. Why should it be? I have turned on a violent interaction. Surely the surface moves.
The shape moves, absolutely. The interaction can push it out along some directions and pull it in along others, grow necks where the free version had none, and give the quasiparticles on different parts of it wildly different masses, as it does in strontium ruthenate. All the geometry is up for grabs.
And what is not?
The volume it encloses. The density of electrons in the crystal fixes the volume in momentum space enclosed by the Fermi surface, and interactions do not change it. Not approximately, the volume is exactly what you would get by filling free states until you ran out of electrons.
That is very strong, and I want to be suspicious of it. Picture before name.
A balloon in a sealed box of water. Squeeze it into any shape you like. A sausage, a dumbbell, something with a neck in the middle. What you cannot change is how much water is inside. The interaction is your hands.
And underneath that is a counting statement, because volume enclosed, in a Fermi sea, is the same thing as number of particles.
Which is why this is adiabatic continuity again, in a form you can put a caliper on. It says the number of quasiparticles equals the number of electrons. none manufactured on the way in, none destroyed. Joachim Luttinger proved it to every order in perturbation theory, which is stronger than the rest of Landau's structure, though not a proof that the series converges. He published it in 1960 in the Physical Review under the deliberately unexciting title Fermi Surface and Some Simple Equilibrium Properties of a System of Interacting Fermions.
And where it is violated, that is a headline rather than a nuisance.
It is the headline. In the underdoped copper oxide superconductors, photoemission sees no closed Fermi surface at all, disconnected arcs with gaps where the rest should be, and no way to assign a volume. That is the pseudo-gap, and it is unsolved. A Mott insulator is a cleaner violation, half-filling, so free electron counting demands a Fermi surface, and there is none because a gap opened.
How was the volume ever tested? The volume enclosed by a surface in momentum space does not sound like something with a dial on it.
Several. The oldest is quantum oscillations. Put a metal in a strong field at low temperature, and its magnetization and resistance oscillate periodically in one over the field, and the period gives the cross-sectional area of the Fermi surface perpendicular to it. Rotate the crystal, repeat, reconstruct the shape. And the timing is lovely. In 1957, the year Landau's Fermi liquid paper appeared in English, Brian Pippard published the first full determination of the Fermi surface of copper by bouncing microwaves off polished crystal faces. It is not a sphere. It touches the zone boundary in 8 directions, so it has necks.
A piece is missing. We have quasiparticles in correspondence with free electrons, but quasiparticles must interact with each other too. What happened to that?
It is real, and it is the last ingredient. Notice why it is now manageable. The quasiparticles that matter live in a thin shell, so there are very few of them. The interaction between them is screened, so it is short-ranged, and their energies are small. We have gone from a dense soup to a dilute gas with residual interactions.
How do you encode that interaction without doing the impossible calculation?
By asking what it can possibly depend on. 2 quasiparticles, both essentially on the Fermi surface. What are the variables?
Both energies are pinned at the Fermi energy. Both momenta have Fermi magnitude. So the only freedom is direction, and the interaction should not care about overall orientation in space, only the relative one. It is a function of a single angle, the angle between them.
One angle. That is the entire remaining unknown, and you got it from bookkeeping. One more binary variable, whether the spins are parallel or anti-parallel, and you have 2 functions of one angle.
And a function of one angle on a sphere, I would expand in the natural functions on a sphere, the Legendre polynomials. So, 2 lists of numbers.
The Landau parameters. And here is the part to state flatly rather than dress up. Those numbers are not derived. Landau's theory does not compute a single one of them. They are inputs. You measure them.
What is the theory for if I have to feed it the answer?
Because there are few of them, and many things they fix. And each has a plain meaning. It answers, what does one quasiparticle feel when another goes past at this angle? Which is the same as asking how stiff the liquid is. The first number in the spin-symmetric list is its stiffness against being squeezed, the compressibility. The first in the spin-antisymmetric list is its stiffness against having its spins pulled one way, the magnetic susceptibility. The second in the symmetric list is tied to the effective mass. 3 measurements in, and a great deal of what else the liquid does is determined.
Which is the effective theory bargain from our first conversation, exactly as you set it out. It does not generate its own coefficients. It buys enormous reach over a stated domain in exchange for a few numbers from elsewhere.
The same bargain, and this is its cleanest instance. And there is a system where it has been tested about as hard as anything in physics, and it is not a metal.
Go on.
Liquid helium-3. Neutral atoms, no charge, no lattice, no impurities, with 2 protons and a neutron, so spin 1/2. A fermion. Cool it below about 1/10 of a Kelvin and you have a degenerate Fermi liquid made of atoms, with a Fermi surface and no solid to argue about. The system Landau built the theory for.
And its numbers.
The quasiparticle mass is about 3 times the mass of a bare helium-3 atom at low pressure, rising to about 6 as you squeeze it towards freezing. The susceptibility is strongly enhanced and the compressibility suppressed by the amounts the corresponding parameters demand. And then there is the prediction nothing else would have made.
Which is?
Sound. Ordinary sound needs collisions. It is a pressure wave passed along by particles bumping into one another, and it needs the fluid to stay in local equilibrium, so its period must be long compared with the time between collisions. Now cool a Fermi liquid. The collision rate dies as temperature squared, so eventually the collisions cannot keep up and ordinary sound should stop propagating. Landau said something else propagates instead. Not a wave of density in a fluid, but a wave in the shape of the Fermi surface. The surface ripples, and because quasiparticles feel each other through those parameters, the ripple sustains itself. He called it zero sound, and it travels at a different speed.
And somebody heard it.
Abel, Anderson and Wheatley, at Illinois, 1966, in liquid helium-3. The sound velocity changes as you cool through the crossover, exactly where the theory says the collisions give out. A collective mode that exists only because the quasiparticles interact, predicted from a framework whose only inputs are measured numbers.
Everything so far has been inference, heat capacities, resistances, sound speeds, all read off through a theory. I want to see one. Is there an experiment that puts a quasiparticle on a screen?
There is, and it is why this subject changed character in the 1990s. Angle-resolved photoemission. The underlying physics is 120 years old. Einstein, 1905, the paper he got the Nobel Prize for. Light of a definite frequency in, electrons out, and their kinetic energy is the photon's energy minus what it costs to escape.
Give me the apparatus as a scene, because the details are the technique.
A crystal in ultra-high vacuum, better vacuum than low Earth orbit, cooled to a few Kelvin. You cleave it inside the chamber, so the surface you're about to interrogate has never met air. Monochromatic ultraviolet light comes in from a synchrotron at a few tens of electron volts, or a laser at 6 or 7. Electrons come off, and you measure 2 things about each: its kinetic energy and the angle it left at.
So I have an energy and a momentum for each electron. What is on the screen?
For each momentum, an intensity is a function of energy, not a spike, a peak of finite width sitting on a broad background. And there are 3 separate quantities living on that one shape.
Take them one at a time.
Where the peak sits, trace it as you sweep the momentum, and you have the dispersion. Compare its slope at the Fermi surface with the slope a calculation that ignores electron-electron interactions gives, and the ratio is the mass enhancement, measured directly, not inferred from heat.
2.
How wide the peak is. Width in energy is Planck's constant over the lifetime. A state that does not live forever does not have a sharp energy. So the width is the scattering rate, read off a screen. Now watch it as you move towards the Fermi surface.
It should collapse, and collapse quadratically, faster than the binding energy it sits at, so the peak sharpens relative to its own position, rather than merely narrowing.
Which is what happens, and it is why I told you in our first conversation that photoemission sees something sharpening where the arithmetic predicts a smear. Your phase space count photographed. You do not have to believe Landau to see the peak narrow.
And 3 is the weight.
3 is the weight. How much of the intensity at that momentum sits in the coherent peak and how much in the hump underneath. That ratio is Z, and be careful with it because it is the number quoted most loosely. The measured intensity is that line shape, which has a name, the spectral function, multiplied by an occupation factor and by a matrix element for the photon to eject that particular electron. And the matrix element depends on photon energy, polarization, and geometry in ways nobody fully controls. So masses and widths are quoted with confidence, absolute weights with caution. The instrument is not the limitation. It resolves a few thousandths of an electron volt routinely, below 1,000th with lasers.
Give me a number I can trust.
Sodium, the occupied bandwidth, bottom of the conduction band up to the Fermi level, measures about 2 2/3 electron volts, where a free electron estimate gives about 3 1/5. So the band is measurably narrower than it has any business being, which means the electrons are heavier than free by about the same fifth that the heat capacity sees, arrived at from a completely different direction.
Let me say what this measures in one sentence. Angle-resolved photoemission removes an electron and reports the energy and momentum it had, and what comes back is a line shape rather than a level. The peak's position gives the renormalized dispersion, and hence the effective mass. Its width gives 1 over the lifetime, and the fraction of the weight in the peak, rather than the background, is Z.
That is it. And notice that all 3 of Landau's modifications, heavier, shorter-lived, less of an electron, are visible at once on a single plot. The theory was written in 1956. The picture of it arrived about 40 years later.
Now the part I have been waiting for. Where does this fail?
In the material that made this whole subject urgent again. And I will give you signatures rather than a description, because signatures are what you asked for.
Signature 1.
The resistivity is linear in temperature, not temperature squared, temperature first power. Michael Gurvich and Anthony Fury measured a lanthanum strontium copper oxide and an yttrium barium copper oxide up to 1100 Kelvin in 1987. And in the lanthanum compound, it is a straight line the whole way, with no sign of flattening. Which was a puzzle by itself, because an ordinary metal saturates once the mean free path gets down to an atomic spacing, and this sails straight past that.
And a linear law contradicts my count at the root.
At the root, which is why it is the right thing to be upset about. Your count used no model. It used energy conservation, Pauli exclusion, and the fact that the Fermi surface bounds a volume in 3 dimensions. If the answer is linear, one of those 3 has to go, and nobody can tell you which.
Signature 2.
Photoemission finds no peak. In the strange metal region, you look at a momentum where a quasiparticle should be, and instead of something narrowing as it approaches the surface, you get a broad hump whose width is comparable to its own binding energy. Precisely the condition that disqualifies a thing from being a particle. Z is not small there, it is undefined, and a number that sharpens both signatures. The scattering rate comes out close to a thermal energy divided by Planck's constant. The fastest an excitation of that energy could conceivably decay. Planckian dissipation. Jan Bruin and colleagues found in 2013 that unrelated materials with linear resistivity all sit at that bound, and nobody knows why it exists.
One caution about the conclusion, because not a Fermi liquid cannot automatically mean not understood.
It cannot, and the counterexample is the one we flagged. One dimension, a chain of interacting electrons, is not a Fermi liquid at any repulsion, however weak. Z is exactly 0, and it is completely solved. What replaces the electron is 2 separate excitations traveling at 2 different speeds. One carrying spin and no charge, one carrying charge and no spin. Inject an electron and it comes apart, and the halves move away from each other.
And somebody has seen that.
Photoemission on chains of strontium-copper oxide shows two dispersing features where an ordinary metal shows one, at the two predicted speeds, and quantum wires show the same separation in transport. So there is a place where Landau's picture fails completely, and the replacement is exact, named and measured. That is the encouraging case. The copper oxides are the discouraging one.
How discouraging.
4 decades, no accepted theory of the normal state. Not several candidates, one of which is probably right. No consensus on what the low-energy excitations even are. That is the last conversation in this series, and I will not pretend it resolves.
Bring me back to where we came in, because I want to dismantle what I walked in with. A wire, a cryostat, and a straight line, when the temperature-dependent part of the resistance is plotted against temperature squared. Let me take that line apart and see whether the hour is inside it.
Take it apart. I will interrupt only if you drop something.
That there is a clean power law at all says the metal has well-defined excitations doing the conducting, and the reason it has them is adiabatic continuity. Turn the interaction up gradually instead of switching it on, and every state of the free gas slides continuously into a state of the real metal. Nothing new is born and nothing dies, so the low-lying states can be listed, and the list has the same length and the same labels as the free systems. 1 unit of charge, spin 1/2, a momentum. The correspondence is the claim, and it says nothing about what those states look like.
With the caveat.
It is not a theorem. It fails if a bound state forms, which is a superconductor, if a gap opens, which is a Mott insulator, or if the perturbation is singular, which happens at temperatures nobody will reach. And it means nothing for excitations too short-lived to be followed while you turn the dial.
Which is what makes the rest work. Now the exponent.
A count of empty seats. The partner comes from a thin shell below the shoreline because it must finish above it, and the only energy on offer is what my excitation brought. Both outgoing states must land above the surface, and conservation fixes the second once the first is placed. 2 squeezes, so the rate goes as the energy squared, and the same count says the quasiparticle gets better as you approach the surface, because its width shrinks faster than its energy does. The theory manufactures its own validity out of a small parameter that has nothing to do with how strong the repulsion is.
One correction. What makes that a resistance rather than a collision rate is the lattice, and only collisions that hand a whole lump of momentum to the crystal cost the current anything. Now the 2 renormalized numbers, because without them this is a story.
The effective mass is how sluggish it is. The slope of energy against momentum at the surface, read as an inertia, because the excitation cannot move without shoving everything aside, like a bubble in water dragging the flow with it. It runs from a quarter above free in the alkali metals to 1,000 times free in the heavy fermions, which are still Fermi liquids. And Z is how much of a bare electron is left in the dressed excitation. Inject one, and only a fraction emerges as the clean, single excitation, the rest spreading out as a shower of pairs. Or, the version I would draw, the free gas has a cliff in its occupation of momentum states, and turning the interaction on erodes the cliff, but leaves a vertical step standing, and the height of that step is Z.
And photoemission puts all 3 on one plot. Position for the mass, width for the lifetime, share of the weight for Z. You have left out only the item that turns description into prediction. Luttinger's volume, fixed by the density of electrons, however the interaction reshapes the surface. And 1 human sentence to close the account. Landau built this out of a symmetry argument, a counting argument, and a refusal to write down a microscopic model. In January of 1962, he was in a car crash and spent months in a coma. The Nobel Prize he was given that year had to be delivered to him in Moscow. He never really worked again.
And let me give you the signatures myself, since spotting one in the wild is the thing I actually have to be able to do. 1. The resistivity is linear in temperature rather than quadratic, and stays linear over a range nothing else could produce, hundreds of Kelvin, down to just above the superconducting transition, with no saturation. That kills the count at the root, because the count says the rate must die as the square. 2. Photoemission finds no quasiparticle peak, only a broad hump as wide as its own binding energy. The condition we agreed disqualifies a thing from being a particle, so Z there is not small, it is undefined. And a third, if I want one, the surface fails to close, and no volume can be assigned to it.
All three, and the first two are independent, which is what makes them worth having.
Let me end on a disagreement rather than a summary, because I do not think you and I mean the same thing by why metals work. You have shown me why the free electron picture survives. You have not shown me why the electrons in an ordinary metal never do anything else. Adiabatic continuity is a hypothesis that the system deforms smoothly. Nothing you have said explains why it does.
Nothing I have said explains why it does, and I would not want you leaving with the impression that it does. Landau's theory tells you what to expect if nothing dramatic happens, and exactly which dramatic things would break it. It does not tell you when they happen. It is a theory of the ordinary case, and its greatest service is making ordinary a precise word, so that you can recognize the extraordinary case when you meet it.
So that is where next time begins. Not a better version of this, but the case this one rules out.
The case this one rules out. Somewhere along that dial, in a great many materials, the system stops deforming smoothly and does something with no counterpart in the free catalogue at all. It picks. Out of a family of arrangements, the laws do not distinguish between. It chooses one and holds it, and every atom in the sample holds the same one over centimeters for as long as you leave it alone.
The sugar molecule from our first hour with 10 to the 23 participants, except, I take it, with 3 things a molecule cannot have: a sharp temperature where it happens, a continuous family to choose from rather than 2 options, and excitations that are slow twists of the choice itself, costing almost nothing.
All three, and a stiffness that makes the whole lump respond as one body. That is the next conversation.
And the thing I should carry out of today while we do it.
That the reason a copper wire behaves like a gas of nearly free particles, while every electron in it is being shoved by every other with an energy comparable to its own, has nothing to do with the shoving being weak. It is that Pauli leaves so few places to go that an excitation near the surface can barely find anyone to collide with. The metal is not quiet. It is jammed, and being jammed is what keeps it simple. Cool a lump of iron with me next time, and we will watch it decide.